Started. So today we're going to finish off chapter 11. We will do chapter 13 after the break. I'll get the slides up. I was planning to work on them on Monday next week, so I'll get them up sometime before then. Yeah, before we actually have lecture. I'll try and get them up sometime during next week. So chapters 10 and 11, the homework is due on the 4th. We'll have the review of the material that will be on the test, which will be mostly chapter 10 and 11 with a splash from chapter 13. And then we'll have our exam on chapters 10, 11, and 13 on the 11th. So review will be on the 9th, the exam will be on the 11th. Today is going to be the last lab. I have your previous labs up here graded. Yeah. So we were talking about angular momentum. So angular momentum is usually expressed as L, and it's moment of inertia times omega. And for a single particle, for angular momentum of a particle, it ends up being mass times velocity times radius, which is linear momentum times radius. Much like other things. So that's a particle moving in a circle. But angular momentum is moment of inertia times omega. The unit is kilogram meters squared per second. For more general motion, if you have some particle that's moving, angular momentum is radius times radius times momentum times the sine of the angle between the radius and the momentum. The radius times mass times velocity times sine theta. That's for a more general motion. And if we look at how angular momentum changes, we end up seeing that the sum of the torques is equal to moment of inertia times angular acceleration, but it's also equal to change in L over change in T. Now, the thing that's most interesting about angular momentum is that because angular momentum is moment of inertia times omega, moment of inertia can change without the mass of the object changing, because it just depends on the distribution of mass. So it's possible for an object to change its moment of inertia, and thus its angular velocity will change because its angular momentum must remain the same. So there will be no torque, but the angular velocity will change. So if you have a disk with a moment of inertia of 15 kilogram meters squared that's rotating at 10 radians per second, what is the angular momentum? Yeah, it's just going to be moment of inertia times omega, so 15 kilogram meters squared times 10 radians per second, 150 kilogram meters squared per second. Now, angular momentum is conserved, so if the net external torque on a system is 0, the angular momentum will be conserved. And the most interesting consequences of this occur in systems that are able to change shape. Which I will now demonstrate for the people who are actually here. Let's hope I don't get too nauseous. Yeah, I showed you a video on Monday, but I'm gonna do it for real. Yep. So let me get this there as high as it'll go. That makes it a bit easier. So I have some masses. So I'm gonna spin myself up. Let's go with this better. Oh, I don't have enough friction with the floor. Spin myself up with my arms out. And then when I pull my arms in, I spin faster, slower, and faster. Ooh. Let's see. Sure. Let me. No. I just needed a moment to like set those down safely. So be warned, you will get dizzy.
Yeah, I'm not as tall as that, I sure.
Uh, One I can spin you up.
Yeah, that does make you.
Um, So you can do that on anything that doesn't. And, and that happens all the time in nature, actually, where if you have things like stars or other collapsing objects, as they collapse inwards, they spin faster. And often that'll mean if you have something that's like a cloud of gas or something, you get to spin fast enough that it'll flatten out. And that's why the solar system is a flat disk. um, and you can abuse this shape-changing effect as a tool. Because there's things like governors that use the fact that you can use it like as something to control rotation rate. Because things will fling outwards the faster you rotate, and you can use that like on a steam engine to control how much steam you're pumping in and power output you get. So as the moment of inertia decreases, the angular speed increases, so the angular momentum doesn't change. You can also solve problems that are like angular collisions, rotational collisions, like dropping a record on a rotating turntable. When you drop the record on, you have something with no angular momentum adding to something with angular momentum, and it's an inelastic collision. They're going to have some combined angular momentum. So if you just had a spinning turntable and you drop a record on it, the whole thing will slow down a little. In an actual record player, when that happens, the turntable's being driven, so there's an external torque. So if I have a governing device that consists of two masses of 10 kilograms of a radius of 5 meters, 0.5 meters, rotating in 10 radians per second, if I then move the masses in to a radius of 0.25 meters, what is the angular velocity? Another thing about that, when you do pull the mass in and end up rotating faster, the momentum is conserved, but it is actually an increase in angular kinetic energy, which is why you have to do effort to pull the masses in. So if You have a governing device that consists of two masses that are 10 kilograms each at a radius of 0.5 meters. So remember, moment of inertia is the sum of mass times radius squared. And they're rotating at 10 radians per second, so that'll let you figure out angular momentum. And if I then move the masses into a radius of 0.25 meters, what is the new angular velocity? Because angular momentum needs to be conserved. So our initial angular momentum will equal our final angular momentum. So moment of inertia initial times angular velocity initial equals moment of inertia final times angular velocity final. Moment of inertia is mass times radius squared added up for each object. So that's mass times the initial radius squared plus mass times the initial radius squared, because there's two masses of 10 kilograms and half a meter. So 2 times 10 kilograms times 0.5 meters squared is 5 kilogram meters squared. And our final moment of inertia will end up being 1.25 kilogram meters squared. That's 2 times 10 kilograms times 0.25 meters squared. So it's a quarter the initial. So our final angular velocity is initial moment of inertia times initial angular velocity over final moment of inertia. So that's 5 kilogram meters squared times 10 radians per second over 1.25 kilogram meters squared, or 40 radians per second. By moving the objects into half the radius, you quadruple the moment of inertia. You quarter the moment of inertia. So you have to quadruple the angular velocity. Yeah, omega. Yes. That's a lowercase omega. The uppercase omega looks like that. So it's the symbol you see for ohms. Unit. The ohm. That's an uppercase omega. With a lowercase omega looks like a W. So we can also talk about rotational work and power. Since we have a torque acting through an angle, that does work. So a torque acting through an angular displacement does work, just as a force acting through a distance does. And the normal work energy theorem applies. Torque acting through an angle is going to increase rotational kinetic energy. Since power is the rate at which work is done for rotational motion, as well as for translational motion, power is work over time. So that's going to be torque times change in theta over change in time, or torque times omega. This is analogous to power being force times velocity. So it takes a good deal of effort to make homemade ice cream, especially if you're using a hand cranked machine. Which is why if you're going to do that, I would suggest motorizing it. So if the torque required to turn the handle on an ice cream maker is 4.5 Newton meters, how much work is expended on each complete revolution of the handle? And how much power is required to turn the handle if each revolution is completed in 1.2 seconds? So remember, so work is essentially torque times delta theta, and power is work over delta t. So torque times delta theta over delta t, or torque times omega. Oh yeah, complete revolution is 2 pi radians. That's a definition. That falls off the definition of a radian. So yes, 1 revolution equals 2 pi radians. So work is going to be torque times angular displacement, torque times delta theta. So that's going to be 4.5 Newton meters times 2 pi, which is 28.3 joules. Power is work over delta T. So that's that 28.3 joules divided by 1.2, which is 23.6 watts. Now, it turns out, so far we've been dealing with rotation as if it were just in a two-dimensional plane. But rotation actually happens in 3 dimensions. Now, anything that's rotating is rotating within 3-dimensional space. So how do we deal with that? Well, it turns out there's a relatively straightforward way to do it. We can treat any angular rotation as being your angular rotation, your angular velocity, and your angular momentum will be along the axis of rotation and in the direction where your fingers on your right hand curl in the direction the object is rotating. So if I have this that's rotating this way, which is counterclockwise for you guys, my hand would curl, my fingers curl in this direction. It's rotating along the axis of rotation in the direction my thumb points when I curl my fingers in the direction of rotation. So that rotation is towards you, out of the board. That's why counterclockwise is positive and clockwise is negative. Counterclockwise is out of the board, out of the page, positive. Clockwise is into the page, into the board, negative. So that's the right hand rule. You take your right hand, you curl your fingers in that direction. And lots of relations, like the torque, that torque ends up being, oops, not P. Torque ends up being force. Oh, let me make sure I get this in the right order. It's force cross. Yes. Cross radius. I think that's right. It might be the other way around. A similar right-hand rule gives you the direction of the torque. If you curl your fingers in the direction the torque would go. And I believe this is actually, the torque as a vector. Just want to make sure I get this in the right order. Yeah, it's radius cross force. So it's a cross product, which generates a vector perpendicular to both the radius and the force, and that points in the direction of the torque. But the easy way to do it is just curl your fingers in the direction the object would rotate. Strictly speaking, you could point your fingers, your pointer finger in the direction of the radius and your other fingers in the direction of the force, and your thumb would point in the direction of the torque. Yeah. And because of conservation of angular momentum, the total angular momentum around any axis has to be constant. And because of this fact that these things are out at angles, you get this funky situation where if you've ever seen like a top wobble or a gyroscope precess, you have some angular momentum and it's being changed by the torque, and that effectively causes it to rotate around another axis to keep, you get the force here plus the angular momentum this way changes it creates a torque this way, basically, and that ends up causing the object to rotate. So there's some kind of unintuitive things that happen because of this. That is the end of the chapter. We finished real early. Oh well, I'll just go through, we'll have the lab and you get to head out early. So a force that's applied so as to cause an angular acceleration is said to exert a torque. The torque due to a tangential force is radius times force. This is the vector version. The general formula for torque is radius times force times the sine of the angle between them. That falls out of this vector version. Newton's second law for rotation is that torque equals moment of inertia times angular acceleration. In order for an object to be in static equilibrium, the total force and the total torque acting on the object needs to be zero. An object will balance when it's supported at its center of mass. In systems with both rotational and linear motion, Newton's second law needs to be applied separately to each of them. Rotational forces, rotational torques and linear forces. Angular momentum is moment of inertia times omega. For tangential motion, angular momentum is radius times mass times velocity. In general, it's radius times mass times velocity times the sine of the angle between the velocity and the radius. Newton's second law can be rewritten as torque equals change in angular momentum over time. And in systems with no external torque, angular momentum is conserved, but because you can rearrange mass easily, changes in angular momentum are relatively easy, so you can get changes in angular velocity without any change in angular momentum. The work done by a torque is torque times angular displacement, and power is torque times angular velocity. It's just work over time. And rotational quantities are vectors that point along the axis of rotation with the direction given by a right-hand rule. Generally, you curl your fingers in the direction of rotation. Your thumb points in the direction that is the vector for that rotation. So that is the end of chapter 11. I'm going to stop there. I'm going to stop the sharing and the meeting, but we have a lab today, the last lab. I have your previous lab here. I will hand out the current lab and then I'll get the stuff out for it. So I'm going to end.